Okay, yeah, so this is how to set up the Vivado system for the TPU. So if you want to make changes to the RTL, you're able to do it. So first, obviously, let's just start from cloning this repository. So the way to do that is I just have a terminal open in the folder I want to clone it to, and just copy the web URL, and then just do git clone. Yep, that looks good. And then from here, you can just go into the compiler. Let's just go into that folder, and then go into the compiler folder, and let's open it up in VS Code. Yeah, and then once you're here, this is the file where you want to run your code. It's the file where you want to run your code. So in this section in main is where you write your code normally. So let's just open up terminal, and the steps to let's run the code first. Let's say you're testing ReLU derivative, so let's just not run this for now, and let's say you wanted to just test. You just wrote simple code to test the ReLU derivative function on the vector processing unit. The instructions to run it are all here. So I'm just gonna follow the same instructions. So we're already in the compiler folder, so let's just create the virtual environment. So let's create a virtual environment. Just wait a bit for that to be created. Yep. And then let's enter the virtual environment, and then let's install NumPy. Nice. Okay. And then, now from here, it's just the same steps. So if you wrote your code, you run the front end first. Yep, this shows the memory map, and then it generates the instructions in here, and also in here. Actually not in here yet. And then you run the back end. Yep, and then you'll see row 4 instructions to here. These are your 4 instructions, and then loads and stores are automatically handled. Okay, and then from here, to run it on the board, make sure you're connected to the VPN, but I'm just gonna copy the commands right now. And then let's go into the board. Yep. Let's just receive the board is there. And then from here, we can copy this command. Okay, so now we see that, there's a bug in this function. One, the expected results should be for these, it should be 0, 0, 1, but this is a really small number, which is not 1, and then 0, 0. So there's probably a bug in the RTL, and then from there, we want to open our RTL source code, which we did clone. So the way to do that is go to Vivado, and then do create project. You can call this whatever. I'm just gonna call it TPU top demo, because these are your top files. I'm gonna store it in the same folder. Yep. Just click an RTL project, We don't need to worry about any of these other settings right now. Yeah, and then to add sources, now this is where you go to add files, and in this you go into here, TPU source code, and then just add all of these files. Okay, so you should see that all these are added. Even though there's no system Verilog, this is fine. Just click next. We don't need constraints right now. Yeah, for the board part, I just wrote it down here. So just copy paste this. Yep. Next. Finish. Yeah, so now you should see that all of our files were copied, and it should have like instantiated it all properly. So TPU top 6 instantiates everything, and then we see all our files. So the first thing we actually want to do is that you see that there's like these question marks here and also here. That's because these we're using the BRAM IPs, and we haven't instantiated them yet. So for BRAM top, this is our like BRAM for like data. So the way you want to do this, we see that this is block mem gen 0. So you go to IP catalog. You search up block memory. Double click. So yeah, so you see that this is block mem gen 0, and this should be the data RAM. So we want this to match the what we're assuming when we're instantiating it. So this is fine. We'll change this to true dual port RAM because we want to do reads and write. Click on common clock. This you don't need to worry about. These are all fine. The write width, these are because we're using FB32. Just set this to 32, and then we're using 13-bit addresses, so 2 to the power of 13 is 8192. This is fine. You don't need to worry about this. And then port B should be the exact same. We don't need to do anything here. If you want, you can enable these two, because it can be kind of annoying when simulating, but yeah, so just double check true dual port RAM. This is the read latency, and address width should be 13, and then we can click OK. Yep, just click generate. Yeah, and this might take some time for you, but I'm just gonna skip ahead to when it's already generated. Okay, yeah, so now it generated, and now we should see that this BRAM is instantiated. So we do the same thing for the instruction memory. So this is block mem gen 1. So we go to the same process. Double click. So we can see that we're instantiating block mem gen 1. So again, interface type native is fine. We want true dual port RAM, common clock. All these are fine. You can leave it. This only difference is our instructions are 64 bits. So just make that 64, and our instruction addresses are 8 bits, so 2 to the 8 or 256. These are fine. Just make sure port B is the same, and then just verify this information. Address width of 8 looks good, and then just click OK again. Yep, click generate, and then yeah, I'll skip ahead to when it's generated. Now you see the IRM is generated as well, so this is good for now. Yeah, and then now we want to see where the bug is. So you can go to compute top, VPU top, VPU op, and then you can make edits to the code. So this is Verilog deriv, and we see that there's a small bug. One is this is true if this is positive, but Verilog deriv, if we're taking, if it's a positive number, you want to return 1, and if it's a negative number, you want to return 0. And this is also not FP32. So yeah, those are the 2 errors. So to fix it, I have an FP32 calculator. So let's say if we wanted to represent 1, we can use this instead. Yep. So let's make this 32-bit hexadecimal. Yeah, that should be good. This is like, I'll just say this is 32. And then the other bug is if we make this, if this is like, so if it's a negative number, then we want to return 0. But we also want to return 0 if the value is like 0. So we can just say, or if operand 0 is equal to 32h 1, 2, 3, 4, 5, 6, 7, 8. Yeah. I think this should be fine. This is okay. Yeah. So then you want to do Control S to save it. And then after this, you can do it in either order. Sometimes you might want to like run simulation and check. Then you kind of want to run synthesis to see that it's like your code is synthesizable. Okay, so I'm just gonna quickly show you how you would test simulation. So on the left, you can just click run behavioral simulation. And just wait for that to load. Yeah, so once you're here, just this is set to 10 nanoseconds for me. You can set it to whatever you want. I set it to 10 nanoseconds. So I like to just type restart in the TCL command console and then just zoom out so I can see like individual clock signals. And then now if I click this arrow, I see like 1 clock signal. And just a cool thing you can do is, at first, if you want to test, you have to force select your clocks with this force clock. So you can just give it 0, 1, period of 10 nanoseconds. And then to force signals, you can just do force like constant and just force it to values. And that's how I test at least. But a cool thing is like, if there's something that you have to like repeat a lot, like let's say you're restarting, asserting your reset signals, you can just copy the TCL commands that happened the first time you do it, and then the next time you need to do it, you can just like copy paste these and then put it here like this. So you can see it automatically did everything. For example, when I was testing like reading data from VRAM, I needed to test I obviously needed to load the data first, and this was annoying to do like manually each time. So I did it like manually once, and then I had the commands saved. So yeah, that's just how you would test simulation. After you've tested it in simulation, you want to make sure it's synthesizable. So just click run synthesis. Yeah, and I mean, you could like skip this part and just wait till we make the block diagram, because that will run synthesis anyway on your design. But it's easier if you know your design is like synthesizable before putting it in, because then you don't have to like go back, repackage the IP, which I'll show you how to do, and change stuff. So it's easier to just run synthesis now. Yeah. Yep. Okay, so now you can just view the reports if you want. I'm not really, because you can see messages. There's one error. This is usually fine. I usually just ignore this. And the warnings can be important sometimes if you want to see like these. but usually all these are fine. Yeah, I mean, these are kind of helpful sometimes, like just seeing ways to optimize it, but I mean, it should work. So that looks good. And then from here, what we want to do is we want to package this into an IP and then like create another project called TPU system where we like instantiate this with the block with the board and the DMA. Yeah, so now I'm just going to show how to package this into an IP. So here you'll see tools. You want to click create and package new IP. Next, package your current project. You can use the default IP location if you want. Just for convenience, I'm going to store it in the same folder that everything is in, just so it's easier to find. And then you can click OK, finish. Yeah, and then you get these packaging steps. This is fine. This is fine. Sometimes you'll see like merge changes from file groups wizard. So you can click OK for that. Just make sure this is okay. These are our AXI ports, so these are good. This you don't have to worry about. And then just click package IP. And yeah, the idea is next time, so yeah, you can see it finished packaging. And the idea is next time you want to make a change, you can just make your changes and then you get an option to repackage the IP. So now that we have the IP ready, we want to create like the block diagram that represents our system. So our board, the DMA, and like our custom IP. So we can go file, project, new project. Let's call this TPU system demo for now. You can store it whatever folder you want. RTL project. We don't need any files. This is all good. And we can get the board part again. All right, finish. I mean, you can close it if you want. I'm just gonna keep it open. Okay, so now that this is open, the first thing you want to do is click on create block design. So you can just call it design 1 for now. That should be fine. Okay. So now that the block design is created, the first thing we want to do is we want to add our IP. So to do this, we need to make sure that Vivado knows it exists. So you can left click here, click add repository, and then click on the folder where you saved your IP to. So I'm going to click this. Yep, and then we see one repository was added. Yep, and this is our custom repository. And then you can click add IP, and then just type in TPU top. Okay, that looks good. So now alongside this, we need to add the board first, and we also need to add the DMA. So again, we click add IP, type in sync. Yep, this is the board. Okay, that looks good. And then add IP, and then click DMA, and it's this one, AXI direct memory access. Okay, I'm just gonna go to this here. Okay, so we do need to configure some settings before we connect everything. So let's configure the board first. So there's two things that we want to change. So first, in PSPL configurations, just click here, go to interfaces, slave interface, go to AXI HP, and then just select this, and then change the data width to 32. Yeah, and then the other thing you want to do is, right now our design doesn't meet timing at 100 megahertz, so go to output clocks, low power domain clocks, fabric clocks, and then instead of a requested frequency of 100 megahertz, let's go 50. I mean, you can experiment and go a bit higher, but let's just be safe and go at 50 for now. So, okay, that looks good for the board. And then for the DMA, disable scatter gather engine, and then change the width of this buffer length register to 23 bits. Average width of 32 looks good. The read channel should be 64 bits because that's just how it's configured and how many bits an instruction is. Max burst size of 8 is fine. These look good. So you can click OK. Yeah, and then TP top, you don't need to do anything. So connection automation should connect everything first. The only things you need to manually connect is on our TPU top, connect our slave interface to this port, the master XC port for the DMA, and then our master interface. Sorry. Yeah, to the slave port of the DMA. Yeah, and then now you can just click all automation, click OK. Yep, there's sometimes more. Just click OK. And then, yeah, so this looks good. The way you can check if this is like all okay is click validate design. Okay, it says validation successful, no errors or critical warnings in this time, which is good. So from here, you can save it by doing Control S. Yeah, from here, the thing is, like, a block diagram can't be directly synthesized. So we need to create what's called a HDL wrapper. So right click here, or no, actually in sources. Right click here and click create HDL wrapper, and then just click let Vivado manage wrapper and auto update. Yep, just wait for a bit. Yeah, so now we have our HDL wrapper with everything instantiated, and then from here you can just go ahead and click generate bitstream. So yeah, you can click OK for this, and yeah, this might take a while, so again, I'll skip to when it's ready. Okay, yeah, so now we see that the bitstream was successfully generated. So you just want to click view reports, and we can, if you're interested in any of these reports, you can click on them. But the important thing is to go to design runs and just make sure that all of these parameters are positive, and that just means our design meets timing. Yeah, so now all we need to do is copy 2 files into our compiler folder. So this is where my thing is. I go to TPU system demo, and then you want to go to hardware. You want to go to gen sources 1, BD design 1, hardware handoff. Copy this and just put it in the compiler in TPU deploy. And go back to the TPU system demo. We also need to get the bitstream and runs implementation 1. This is the bitstream.
So copy this. View, compiler. Yep. And then you can just delete these two. And then just rename these. Oh, wait. So you can just delete these two. And then just rename these two. Handoff.